Good morning, everyone. Welcome back to Fundamentals of Engineering with Farhad Mechanics of Materials Maximum Deflections Calculation. So we want to solve this interesting problem, which is a cantilever beam handling a distributed load of W. We want to calculate the angle of rotation at free end theta and also the maximum deflection of beam delta. Last time we have solved this problem with the help of integration method, which is a long solution, and this time we want to solve it with solution 2, which is the moment area method, which is a much faster solution, and it's very efficient for multiple choice question and also in solving it with different approach. So we need to draw based off the name of the method. We definitely need the moment diagram of this beam. If we draw the shear diagram, we do know that there is a reaction here, and that reaction R sub A is equal to this distributed load. So the V shear diagram of this is the shear diagram, which starts from the WL at the support, and it just moves downward to reach zero at the free end. There is no shear here. And then the area under the shear is the amount of moment. And if we just divide the moment by EI, that's the second degree curve also, that's M over EI and is equal to Y double prime. And the theta at B with respect to A is equal to theta B minus theta A. We do know that because it's fixed, there is no theta at A, so theta at A is equal to 0. So this one definitely goes 0. And we do also know from the first moment area theorem that the theta B with respect to A is nothing but the area under M over EI, which is if the shear is linear, the moment is second degree, and the area under the shear is the amount of moment at here. So this is WL. Area of this triangle is a half of WL times L. So that's WL squared over 2 divided by EI to get Y double prime. And in that sense, it just says M over EI, which is this yellowish area of the second degree. And we do know the area of a second degree curve with this characteristic is 1/3 of the base, 1/3 WL squared over 2EI times the length, which is the length of the entire span. And it just make it like WL cubed over 6EI. That's our theta at B. And for calculation of delta or maximum deflection, you can easily see the traveling downward of the free end of B, that's delta, and that's equal to tangential deviation of B with respect to A. We call it TBA, and that's the second moment area theorem, and it just says the tangential deviation of B with respect to a horizontal line passing through the A, that's equal to maximum deflection. And second moment of area theorem, it just says that's nothing but area under M over EI times X bar. And X bar is the distance of centroid to the vertical line, which is here. That's 3/4 of length for a second degree curve. So if you don't know what X bar is, delta BA is equal to TB with respect to A. And then if we have our distance from the centroid to the vertical line passing through B, and delta B is equal to tangential deviation of B with respect to A, we can easily calculate the delta B, which is TB with respect to A. This is the area part, this is the area part, and that's the This is the area part of our m over ei. This is the area under m over ei. And the other part is 3/4 of L is the distance of the centroid to vertical line passes through B. This is the area part, m over ei, and it just makes it like WL to the force over 8 EI. You can see how this method is faster than the classical method, which is the integration. You have to come with the equation of moment and then integrate it twice to get the delta from moment. And this is far faster and gives you the delta and theta much faster. Thank you. We'll solve the same problem with the third solution in next video, and that's Castigliano's theorem. Thank you.